All right, what we have is a ballistic pendulum, and we are trying to find the initial velocity of the projectile, which is a steel ball. So you can see the picture here. The pendulum is hanging vertically, which has a mass big M. The ball is fired with the velocity u, whose mass is small m. And after the collision, the ball and the pendulum, they both move together. So basically we have a completely inelastic collision because there's going to be energy loss in this collision, but we can still apply conservation of momentum for the collision. Now after the collision we can apply conservation of energy, because we can assume that there is no friction or air drag. So if we apply the conservation of momentum first, basically we will apply the conservation of momentum before, which is this. The ball is moving with the velocity u, the pendulum is at rest, and then after the collision they both are moving with the velocity v. So basically we are going to equate the momentum for both. All right, so I'm going to put an equal sign, and on the left side I'm going to write the momentum before the collision. Now before the collision only the ball is moving, so only ball has the momentum, so it's going to be just small m times u. That's all we got. Now after the collision, both are together, so I'm going to write small m plus big M, and now they both are moving with the velocity v, so I just put v for that, capital V. So we can find out what is u now. So u will be equal to small m plus big M divided by the small m, and then we have the v. So to figure out this u, we need to know what is v is. All right, so for that we're going to apply the conservation of energy. So I'm going to use a red color for that. So how do we apply the conservation of energy? Well, once again we have an equal sign, and we are going to put the energy at the end goes on one side, and the energy uh, at the beginning just after the collision goes on the other side. So we're going to equate those two energies. Now just after the collision, the energy we do have kinetic energy, plus we do have some potential energy because there is some height h1, and then after the collision we have only potential energy because the pendulum comes to rest at height h2. So what is kinetic energy? Well, it's 1/2 the mass. We have both of them, small m plus big M, and then the velocity is of course v, so v squared, plus the potential energy is going to be small m plus big M g h1, and then potential energy at the end is going to be small m plus big M g h2. So this is the expression we get for conservation of applying conservation of energy, and we apply this only after the collision. Now how do we simplify this? Well, if you look very carefully, the m plus m is common everywhere, so we can cancel that. So let me use a different color for that. So we can cancel this, this, and this. So what's left is 1/2 v squared plus gh1 is equal to gh2. So now I'm going to move my gh1 to the other side. So 1/2 v squared will be equal to gh2 minus gh1. Okay, then I'm going to multiply by 2, so v squared will be 2 gh2 minus gh1. So v is going to be square root of all that, and you can also take out the g there, so it will be just h2 minus h1 g, like that. Now what I'm going to do is take this v and put it for this v right here. So then u equals small m plus big M over small m, all of it multiplied by v, but v we just derived over here, so I'm going to put that for that. So that'll be just square root of 2g h2 minus h1, and that's on the top. So that's the expression we have for the initial velocity of the projectile. So measuring h1, h2, and the mass of the ball and mass of the pendulum, you can calculate that. All right.